Okay, so let's get started again. Unfortunately, I have a lot of material to cover, so I'm going to be relentless and move quickly. Let's see. I guess I'll keep this definition for the moment. The next thing I want to do is just explain briefly an application of the Lorenzian inversion formula and point out why the fact that the double commutator appears, why the fact that this double discontinuity appears is really interesting and important. So the application that I'll talk about is the light cone bootstrap. This will give us an example of the inversion formula in action. So the physical question that we're going to ask is, what does the CFT spectrum look like at large J? So at large spin. So we can, to answer that question, you can just take the Lorenzian inversion formula and set J to be large and then start analyzing what the integral looks like. So the integral in the inversion formula is over a square, z and z bar between 0 and 1. The only place where J enters is in this funny conformal block. And by the way, the reason that the conformal block is funny is because dimension and spin have been swapped with each other. So usually in the conformal block, dimension is the first argument and spin is the second. But here they're swapped in an interesting way. And we'll talk a little bit more about that later. So I'll also write the measure factor here. We have this. So we have this thing appearing in the inversion formula, and you might remember that the conformal block goes something like z bar to the delta over 2, but here delta and j have been swapped. So instead of going like z bar to the delta over 2, it goes like z bar to the j over 2. And so what that means is that this funny conformal block in the inversion formula at large J gives something that's very suppressed down here and growing as you move away from the origin. So setting large J pushes the integral away from the S channel towards the T channel. But there's another thing going on in the inversion formula, which is that, so if we're interested in the actual OPE data of the theory, then we want to know about poles in this function C of delta J that the inversion formula computes. And poles can only come from this region or this region. So there's a symmetry under swapping z and z bar, so I'm just going to focus on the upper triangle in this picture. The idea is that poles come from this region where z is small in this upper triangle. So if j is large and we're still trying to compute poles, then we get pushed towards this corner of the square. And this is the so-called double light cone limit. And so the idea is that to understand what the CFT spectrum looks like at large J, you just have to approximate the inversion formula in the double light cone limit. Okay, so that's what we're going to do. The first point is that so here we're interested in small z. And you might remember from the first lecture, a while ago, I wrote a formula for what conformal blocks look like at small z. They're equal to some power of z times a hypergeometric function of z bar. So we're going to take that formula and plug it in here for all of this stuff. And we find that all of this stuff goes like z to the minus delta minus j over 2 minus 1, 1 over z bar squared times this hypergeometric function of z bar. This hypergeometric function, it's a 2f1 hypergeometric function that I called an SL2 block. Maybe I'll write it again just for reference. So it's defined as x to the h, 2f1 of h, 2h, x. Okay, so all this stuff gives us this quantity out front in the region of small z that we're interested in. So that's the measure in the conformable block and the inversion formula. Now let's talk about the double commutator, the double discontinuity of the 4-point function. So the idea now is to say, well, we're trying to compute C of delta J, which describes the OPE data appearing in the S channel. Let's plug in the T channel conformal block expansion and see what we get. So the T channel conformal block expansion is another expression for an expression for this G of Z and Z bar. And it's the right-hand side of the crossing equation that I wrote in the first lecture. So the conformal block expansion in the T channel starts with the unit operator, which just contributes 1. And then there are other operators that appear that are not unit operators. And again, we're interested in the double light cone limit. So what I'm going to do is write these T channel blocks in the limit of small 1 minus z bar. So here for this term, I used the limit of small z. For the T channel blocks, I'm going to use small 1 minus z bar. And so when we do that, we again get to use this formula, but it looks slightly different. So we have OP coefficient squared, and now we have 1 minus z bar to a power, and that power is tau prime over 2 times k delta prime plus j prime of 1 minus z. And here tau prime is the twist of the T-channel operator. And I'm using primes to indicate quantum numbers in the T-channel conformal block expansion and unprimed things to be quantum numbers in the S-channel. So we're going to plug this in. It's a sum over primed operators, and we're going to obtain a function of delta and j. So now what we're supposed to do is take this thing and compute the double commutator from it, which means we need to take this double discontinuity. So the double discontinuity is a linear combination of analytic continuations around z bar equals 1. And when we take this term and we analytically continue around z bar equals 1, we just get phases. E to the 2 pi I times tau prime over 2. And actually, we have to be a little careful. There's another 1 minus z bar over here. So we get e to the 2 pi I times tau prime minus 2 delta phi over 2. So that would be one way of going around the singularity. We can go around the other way, or we cannot go around at all. So we use this formula. And you find that d disk of the interesting quantity that depends on z bar, so that's tau prime over 2 minus delta phi, is equal to 2 sine squared of pi times tau prime over 2 minus delta phi times the same power of z bar. Okay, so the double discontinuity just takes the conformal block expansion and inserts in it a bunch of factors. And these factors are positive and bounded. So it does something very non-violent to the conformal block expansion. It just inserts a bunch of extra positive factors into the T-channel conformal block expansion. So that's not too bad. And the fact that these factors are positive is actually very important for some of the really nice properties of the Lorenzian inversion formula. So this double discontinuity, even though it's a linear combination of analytic continuations, in the end you find that, so the OP coefficients here are positive, the sine squared factor you get here is positive, and the OP and the conformal cross ratios are in this square where all these various powers and hypergeometric functions are positive. So the whole thing is positive. And this positivity is a very powerful tool for learning things about the structure of C of delta J. This positivity can be used to prove some interesting results, one of which is the average null energy condition, which I might have some time to talk about, I'm not sure. Another which is Nachtmann's theorem, which is a statement about the shape of anomalous dimensions as a function of spin. There's all sorts of interesting things that come from this positivity. It's really important and beautiful that Karen Ho found this nice positive object hiding inside a Lorenzian 4-point function. Okay, so let's just take this thing and plug it in to the inversion formula and keep going with our computation. So the idea is that so what do we get here? So we get a contribution to C of delta J from the unit operator, for example. So it involves these factors in front of the inversion formula. This factor that we get from the double discontinuity. And here I'm going to look at the unit operator contribution. So I'm taking this term just for simplicity. So the tau prime is 0. So we just get sine squared of pi times delta phi. And then we have two integrals to do. We have an integral over z and an integral over z bar. And this integral over z is z to the delta phi minus delta minus j over 2. And the integral over z bar is of this SL2 block, this hypergeometric function, times some power of z bar and 1 minus z bar. So the integral over z bar is just a beautifully well-behaved integral. It can be done exactly in this case, but that's not really so instructive for us. So basically just it's an integral between 0 and 1. This is a function that is very nicely behaved between 0 and 1. So it's basically growing like this. So that's k delta plus j. And as you increase j, this function is more and more suppressed. And then this thing also looks kind of like that. So there's another thing like this, which is z over 1 minus z to the delta phi. And depending on delta phi, this can have a singularity at z equals 1. And you have to treat that singularity carefully. In practice, the thing that you should do is compute the integral assuming delta phi is in the regime where there's no singularity, and then analytically continue from there. And you can ask me later why that's the correct prescription. But the upshot is that this integral can be done, and it has a perfectly nice form. The interesting thing for us is this integral. What the z integral leads to is just a pole 1 over delta minus j minus 2 delta phi. So we get that times the result of the z-bar integral, which is some function of delta plus j. And roughly speaking, it looks something like, so at large j, it looks something like 2 to the minus 2j, j to the 2 delta phi minus 3 halves. So, so that's the contribution of the unit operator at large j. And so now we can ask, what about other operators? And the point is that these other operators come with these extra factors, 1 minus z bar to the tau prime over 2. And that means that, so when we insert these extra factors into the z-bar integral will, oh, good. So what do these extra factors do? Well, they're small over here and rising over here. So we get these extra factors here that look like this, 1 minus z bar to the tau prime over 2. And you can see that as j gets big, this thing is going down, and so its overlap with this thing is getting smaller. And the rate at which the overlap decays at large j, it's faster and faster if tau prime is big. So if tau prime is really, really big, then this term is peaked over here. And if j is really, really big, then this guy is peaked over here, and they have basically no overlap with each other. So if you work this out, you find that you get a correction to the contribution of the unit operator. Well, let me write it slightly differently. If you look at what other operators contribute, you find that you get something like a double pole that comes from the z integral. The z integral is slightly different because you have to integrate this. You have this hypergeometric function appearing here instead of just this power. So you end up getting a double pole. And then times this same 2 to the minus 2j, j to the 2 delta phi minus 3 halves, and then an extra 1 over j to the tau prime. So the point is just that the contribution of other operators is suppressed at large j, and the amount of suppression depends on the twist of those operators. So an operator of twist 1 gives a contribution that is down by a power of 1 over j compared to the unit operator contribution. This is just what some elementary analysis of these integrals tells you, but it has a really interesting physical implication, which is that at large j, there are these poles in C of delta j, which means that there are operators at delta equals 2 delta phi plus j. So there exist operators at delta equals 2 delta phi plus j. What the double pole leads to are anomalous dimensions for these operators. So they then have some anomalous dimensions that are functions of j, and these anomalous dimensions die off like 1 over j to the tau prime. So the anomalous dimension as a function of j looks like 1 over j to the tau prime. This is a universal result about any conformal field theory at large spin. These operators automatically have to be there. These are so-called double twist operators. The idea is that the twist of these operators, delta minus j, is approximately equal to 2 times the twist of the things we started with, delta phi. And the general statement, the general thing that you can prove is that if you have 2 operators in a CFT, O1 and O2, with twists tau 1 and tau 2, then there exist double twist operators with twists there exists an infinite family of double twist operators at large spin whose twists approach tau 1 plus tau 2. And you can take this result and iterate it. So you have, let's say now you take a double twist operator and you have some other operator, you can consider the OPE of those guys and now find that there have to exist triple twist operators and so on. So this is telling you about some structure of the CFT spectrum at large J. And these results were known before the inversion formula from some somewhat complicated analysis of the structure of the crossing equations. And one of the beautiful things here is that this gives you the existence of double twist operators with very little work, and furthermore gives you a completely systematic way to compute all corrections in 1 over j to their anomalous dimensions and OP coefficients. So that's something that took a long time to develop, called large spin perturbation theory for CFTs, and the inversion formula just completely automates large spin perturbation theory. Yes?
Excuse me, a very technical question. So it seems to me that the second term is sort of a second order pole, so I should have a log of j as well, right? I mean, you wrote that gamma j is simply 1 over j tau prime, but it seems to me that it should also have a log of j as well.
So what this double pole means is that when you close the delta contour, then you end up with derivatives with respect to delta. And those get interpreted as anomalous dimensions. There's no log of j here, necessarily.
Yeah, because you have a j2 delta psi, and then if you do the derivative, and delta phi as a constant, it's not.
Yeah.
Okay, sorry.
This is the external operator dimension. Okay. Any other questions? Okay, this gives you a completely systematic way to do large spin perturbation theory, and one of the things that's been going on over the last several years is people have understood that large spin perturbation theory and now the inversion formula, which pretty much subsumes it, is a very efficient way to solve the crossing equations. So you might be interested in a particular theory. You use what you know about that theory to constrain the form of the 4-point function. And then you plug into the inversion formula and use that to relate CFT data to itself. And you can use this to make progress in computing anomalous dimensions and OP coefficients of operators in lots of different theories. So this is a really powerful tool for analyzing the crossing equations. And I wanted to say one more thing about really why it's so powerful and why people have gotten so much mileage out of it in recent years. It really has to do with this factor. So this factor came from the double discontinuity, and it means that there are certain operators that don't contribute to the double discontinuity, or contribute a very small amount. And the idea is that if you had an operator with twist tau prime very close to 2 delta phi, then its contribution to the double discontinuity is suppressed by this factor. And we just learned that there are lots of operators like that in CFTs. So these double twist operators are completely ubiquitous. They're necessary for solving the crossing equation, but they don't contribute to the double discontinuity. So you, at least at leading order. So instead what happens is that this factor, if tau prime is 2 delta phi plus gamma, then this factor goes like gamma squared. So this kind of thing lets you bootstrap theories where the double twist operators have small anomalous dimensions. You start by doing a computation at some where you approximate the double twist operators as just not contributing to the double discontinuity at all. you plug that in, and you get expressions for the double twist anomalous dimensions. And now you can plug those back in and include the gamma squared corrections to your computation. And this technique lets you use the inversion formula to bootstrap large N theories and also weakly coupled theories. And those are the two arenas where people have sort of made the most progress with these analytic bootstrap techniques.
Sorry, can you, so let's say we establish now that there are these double twist operators in the OPE.
Yeah.
Can you quickly establish the necessity of higher twist operators in the OPE, in the same OPE, so that we have to include a...
So you mean the double twist operators with the plus 2n?
No, with more than two deltas.
Yeah.
Triple twist. And
yeah, absolutely. So, yeah, you can do that. So basically what we did here is we analyzed the contribution of individual conformal blocks. We took one conformal block, plugged it into the inversion formula, and we got this structure. If you instead take a family of conformal blocks, say a double twist family, and do the sum over the double twist family first, and then plug it into the inversion formula, then you'll spit out multi-twists of all kinds.
Sorry.
Yes.
Are you making any assumption about the unitarity of the CFT for these general bounds?
Yeah, good. So one assumption, yes. So I am using unitarity in that in saying that the contribution of these other operators are suppressed relative to the unit operator. So the unitarity tells us that there's a twist gap in the theory. Tau prime has to be bigger than d minus 2 for non-scalar operators, or d minus 2 over 2 for scalar operators. And that means that the contribution of other operators is necessarily smaller than the contribution of the unit operator at large spin. If we didn't have those unitarity bounds, then we wouldn't necessarily be able to say that this is a small correction to this. Yes?
So if you play this game for a free theory, then everything needs to resum up to 0 for the anomalous dimensions, right?
Yeah, that's right.
Is this understood how this happens?
Yeah, absolutely. The way it happens is that the free theory has essentially only double twist operators in it. So d-disk is 0. And so then you plug that into the inversion formula and you find 0 anomalous dimensions for the... sorry, I said that too quickly. D-disk of everything that's not the unit operator is 0. So, but the answer you find is that you take d-disk of the unit operator, plug it into the inversion formula, and that gives you back precisely just this term with no anomalous dimensions. Okay. Other questions? Yes?
Perhaps I haven't quite understood. Did you use crossing symmetry to derive that?
Yeah, I sort of did implicitly. So the idea was that the inversion formula comes from the fact that we know there's an S-channel conformal block decomposition, and we're trying to invert it and figure out what's there. Then I took the formula and I plugged in the T-channel conformal block decomposition. So in that way, you use the fact that both conformal block decompositions exist at the same time for the same function.
Sorry, coming back to the free theory. So if you have something like phi square, you don't have only unit operator in the double.
Yeah, a 4-point function of phi squared.
I think that was the question.
Oh, I see. Yeah, that's true. Yeah, that's right. So I think what must happen is, so I wasn't very precise about how this double pole comes about, but the double pole really comes from this hypergeometric function. It must happen that in free theories, when you actually look at what appears in the T-channel, you find that the hypergeometric functions sum up in such a way that they don't have a log near z equals 0. So Sasha's right. There is an interesting thing to check in correlators, not of the fundamental field, but of, say, a 4-point function of phi squared or phi to the 1,000 or something like that. Okay. Any more questions? Okay. By the way, just as a concrete example of the power of this factor, so if you try to use the Lorenzian inversion formula for the Wilson-Fisher theory in 4 minus epsilon dimensions, then to leading order, if you look at a 4-point function of phi operators, to leading order, the things that appear in that 4-point function are phi squared and higher spin. So basically, all the operators that appear in that 4-point function to leading order look like something like this. It's a fact that phi squared gets an anomalous dimension at 1 loop, and everything else gets anomalous dimensions at higher loops. And so what that means is that if you plug the 4-point function in the Wilson-Fisher theory into the inversion formula, you find that the unit operator and phi squared contribute up to order epsilon squared, up to order epsilon cubed, and then all of the rest of these things contribute at order epsilon to the 4th. So you get the full answer for the anomalous dimensions of all the operators in the theory to order epsilon cubed by just plugging 2 terms into the inversion formula. So it's way better than doing 3-loop Feynman diagrams involving operators with large amounts of spin. It's spectacularly efficient at solving that theory. Okay. So I hope I've convinced you that the inversion formula is a useful tool. And so now I want to sort of start heading towards proving it. Along the way, for proving it, we're going to try to understand one of its most surprising features, which is this analyticity in spin. The fact that the CFT spectrum at different spins is somehow connected to each other. So this analyticity in spin means that basically there's a larger structure attached to a CFT than you might have naively thought. So there's a nice way to plot the CFT spectrum, which is so we're going to look at the poles of C of delta J. And we're going to plot them with J on the y-axis and delta minus d over 2 on the x-axis. And the reason for this shift in delta is that C of delta J is shadow symmetric. So this plot is going to be left-right symmetric. Yes?
Just a question. You were talking about using the Lorentzian inversion formula for the Wilson-Fisher fixed point. But the Lorentzian inversion formula is only valid for Lorentzian signature, right? Not for Euclidean signature, or does it work for both?
The Lorentzian inversion formula computes this function from an integral over Lorentzian configuration. The function contains in it the OPE data of the theory, which you can use to evaluate correlators in Euclidean or Lorentzian signature. Any other questions? Okay, so just to so one can make this plot. On this plot, there is so there's some unitarity bound. So there's a unitarity bound that says that for local operators, delta is bigger than j plus d minus 2 when j is bigger than 0, say. So this is unitarity bound, and local operators satisfy the unitarity bound, and so they sit they sit somewhere to the right of this dashed line. And one important local operator is the stress tensor with dimension d and spin 2. And then there will be other operators that are necessarily to the right of the unitarity bound, and they're all points on this plot somewhere. Well, okay, so there are these operators, but we know that C of delta J is shadow symmetric, so we also have to draw the shadow images of all of these things. But the statement of analyticity and spin is that actually there are curves that go through all of these points. So the CFT spectrum is not just associated with a bunch of points in this delta J plane, but it's really associated with a Riemann surface in that plane. There's a Riemann surface inside the delta J plane. The local operators are points on that Riemann surface that exist at positive integer values of J. But the whole surface is there. And so you can ask, what is the rest of the surface? What does it represent in the theory? And that's one of the questions we're going to try to answer.
So that line passes through the point, no?
Yeah. The lines should always pass through the points. Yeah.
So David, you cut it off at j equal 1 because of...
Pardon?
You cut the curves at j equal 1?
Yeah, great. Okay, good. So that's right. So the Lorenzian inversion formula is valid for j bigger than 1. And for j below 1, we don't really know what the picture is. And I don't want to spend too much time on this, but I think the expectation, my expectation is that the Riemann surface still exists below j equals 1, but it has some interesting structure that is not well described by the inversion formula that you could only really understand if you figured out how to efficiently analytically continue the inversion formula below j equals 1. Okay, so there's an interesting question of what physics is associated with this regime below j equals 1 and how do you access it. But I think that the Riemann surface should exist down here. We just don't know what it looks like. Okay, so I want to answer this question. What is the rest of the Riemann surface? What is it doing and what's the physics associated with it? Unfortunately, to do that, I need to now introduce a bunch of technology. So you're going to have to bear with me again while we go through some technical things. But this will be useful because it will actually start to introduce some classic facts about CFT in Lorentzian signature that I really should make sure I say during this lecture. So what we're going to do now is we're going to try to work our way towards understanding what the rest of this Riemann surface is, and in particular what it means to have non-integer j. What that could possibly mean, an operator with non-integer j. Okay? First, it will be useful to describe operators in a slightly more efficient way. The tools for doing this are the embedding space. So I'm going to introduce the embedding space in Lorentzian signature and then talk about how to use it to describe operators with non-integer spin. So the idea of the embedding space is to realize Lorentzian space as some kind of subset of the projective null cone in 2 higher dimensions. And so what those words mean is it's the set of points x in Rd, 2 such that x squared equals 0. And projective means that we mod out by rescalings of x. And so to be a little more precise, I'm going to use light cone coordinates for x. So x plus, x minus, x mu, where mu runs from 0 to d minus 1. And the norm on this space is x dot x is equal to minus x plus, x minus, and then the Lorenzian norm on the remaining coordinates. So the projective null cone in this space is topologically S1 cross SD minus 1. I'll leave it as an exercise to show that. Basically, what you should try to do is solve the equation x squared equals 0 using a unit vector in d dimensions and an angle on the circle. Okay, so that's an exercise. So this is not an appropriate space for field theory to live on because it has closed time-like curves. The S1 is time-like direction. So the actual space that that a Lorenzian CFT lives on is the, so if I call this, the actual space that Lorenzian theory lives on is the universal cover of the projective null cone, which is sometimes written like this. Another way of thinking of it is it's the universal cover of conformally compactified Minkowski space. So the tilde means universal cover, and so I'll use this notation. MD is Minkowski space, and the tilde means universal cover of the conformal compactification. And what that means more precisely in this context is it's just taking this S1 and replacing it with R. So this becomes R cross SD minus 1. And this is sometimes also called the Lorenzian cylinder. So it's a theorem due to Lucier and Mack that correlators of a CFT and Lorenzian signature can actually always be analytically continued to live on this space. So you don't have to just sit in Minkowski space. You can think of your correlators as actually living on this larger space. And I'll say how Minkowski space is embedded in here in a second. And that will be actually extremely useful. We'll use that a lot. So I think a picture will probably help make this clearer than anything else. So Minkowski space is a particular patch in the embedding space, and it's described by these coordinates. So here, this is a point in Minkowski space. And you should verify for yourself that if x is a point in Minkowski space, then this point in the embedding space satisfies this condition that, that x squared equals 0. That capital X squared equals 0. And the picture here is that, so the Lorenzian cylinder is R cross SD minus 1. And Minkowski space is a patch on the Lorenzian cylinder, parameterized by this X. So this is Minkowski space. And what I've drawn here is the Penrose diagram for Minkowski space. And for simplicity, I'm pretending that everything is in 2 dimensions. So if we have the Lorenzian cylinder in 2 dimensions, this direction is in S1. So these lines are identified with each other. This coordinate x here covers a patch that looks like this. And so for example, there's a point at space like infinity, which is what you get if you start in the middle of Minkowski space and you move and you take x to be very large in a space-like direction, that's this point. But because we're on a cylinder, this point is actually identified with this point. They're the same point. And that's maybe familiar to those of you who study CFT, that there's a single point at infinity. In this case, it's that there's a single point at spatial infinity, but there are actually different points at time-like infinity. And the entire Lorenzian cylinder is actually tiled by copies of Minkowski space. So this is a Minkowski patch, but there's another Minkowski patch that we could draw, which looks like this. So here's half of it, but this picture wraps around, so the other half is over here. So that's a Minkowski patch, and then here's another one that looks like that. And there's a nice operation that you can do. So if you take a point in Minkowski space, let's say this point, then there's a distinguished point in each of the other Minkowski patches with the same coordinate, with the same little x coordinate as this point. And the way to find it is by starting with this point and sending light rays in all directions. And you'll find that the light rays will go around and they'll reconverge somewhere. And the point where they reconverge is this next sort of image point in the next Minkowski patch. So let's do it. So we start with this point and we send a light ray off from this point, and it goes off this way, and then it, let's see, it wraps back around. So I didn't draw my picture very well. So this is identified with this part. The light ray wraps back around like that. And now let's send a light ray out in another direction. Let's send one out this way. It goes off this side, and it comes back in this side. And so you can see it intersects the first light ray here. And so this is a two-dimensional picture, but in higher dimensions, the same would be true. There'd be the entire future null cone of a point, goes out, wraps back around, and becomes the past null cone of a new point. And so if this point is x, then I'm going to call this point here tx. T is an operation that moves a point to its cousin point in the next Minkowski patch. And then there's also T inverse x, which would be down here. So all of these points, x, tx, T inverse x, are, well, let me be a little more precise. So these 2 points here, points that are connected by 2 of these translations, are actually equivalent in the embedding space. They have the same capital X. But they become non-equivalent when you move to the universal cover. So the universal cover is important for sort of unwrapping the circle and making all these points different from each other.
David, question?
Yes.
So you ended up with Lorentzian cylinder by starting with this Minkowskians and taking the cover, but we could have also started with Euclidean CFT and the radial quantization and do weak rotation.
Yes.
So is there any difference between the two?
No, they lead to the exact same space. And that's actually a really nice way to see why CFT correlators can always be extended to the Lorenzian cylinder. So what Sasha suggested was starting with the Euclidean correlator in radial quantization. So we know in radial quantization, you can do a conformal map that maps the theory to SD-1 cross R, where R is a Euclidean direction. And now we can just take that Euclidean time direction and Wick rotate it to become a Lorenzian time direction. That's another way to get to the Lorenzian cylinder. It's another perfectly valid way of doing things. And it shows why your correlators should be well defined on that space. Any questions? Okay. Good. So this operation of taking x to tx in terms of embedding space coordinates, tx is actually equal to minus x, minus capital X. So again, the embedding space coordinate doesn't fully specify the point on the Lorenzian cylinder because the Lorenzian cylinder is the universal cover of the projective null cone in this space. Okay. Now let me talk about describing operators. I'll first talk a little bit about operators not in the embedding space and then lift them to the embedding space. Okay, so let's talk about an operator with spin. And so remember, our eventual goal is to understand what this Riemann surface is, in particular what the points of non-integer spin are. So we're interested in the question of how do you make sense of an operator with non-integer spin. And so the first step is to use something that is also useful for integer spin operators. So I'm going to start with an integer spin operator. And let's, for simplicity, suppose that it's a traceless symmetric tensor. So it has j traceless and symmetric indices. And it's very useful to introduce a null polarization vector and contract that with all the indices of this operator. So let's define something that is now a function of both x and z. So z squared is equal to 0, and z is some vector in Minkowski space, and we'll take it to be future pointing. And this is a useful thing to do because this object, O of x comma z, it's a completely equivalent encoding of all of the information in this guy. So I told you how to get O of x comma z from this operator, but you can actually go back from O of x comma z to get the underlying tensor. The way that that works is you basically, you take this thing, this is some polynomial in z of degree j, so you just try to strip off z. When you try to strip off z, you'll find that there are ambiguities because z is null. But those ambiguities can be fixed by demanding that the tensor you get is traceless. So let me give you an example. So suppose that we have a traceless symmetric tensor, f mu nu, and we know that f mu nu z nu is equal to v dot z squared, where v is some vector. So can we write down what this is? So yes, so let's just take this expression and try to strip off z. We see that we get v mu v nu, but because z is null, we could have alpha times eta mu nu. And alpha is not fixed by the requirement that when we contract this thing with z, we get this thing. But we know we want something traceless. So tracelessness implies that alpha is minus z squared, minus v squared over d. So there was a unique way to go from this expression to a tensor, a traceless symmetric tensor. And that generalizes to j indices. So so far, this is just a more compact way of writing this operator. And again, by construction, O of x comma z is a polynomial in z with degree j. So it has some homogeneity. O of x comma lambda z is lambda to the j O of x comma z. Okay, so I'll just tell you the punchline now for describing non-integer spin operators. The way you describe non-integer spin operators is that, first of all, instead of writing this funny O, we're going to write this funny O. That's just notational convention. So I'll use this to mean something that could possibly be non-integer spin. And then the other thing we do is just erase that. Okay? So a non-integer spin operator is going to be an operator, funny O of x comma z, that is homogeneous of degree j in Z, but where J could be some complex number. So in this case, funny O of x comma Z is a function of Z, but this trick up here doesn't work anymore. So there's no way to go from this thing to an underlying tensor. So in order to even talk about non-integer spin operators, we're forced to use this index-free formalism, where we think about them as being functions of a point and a null direction. Okay, any questions about that? Okay, so you might be asking, like, why do I care about this kind of thing at all? One of the things I want to explain next is that actually these kinds of things show up in a very natural way just by building them from integrals of local operators. We don't even have to do anything fancy. They're already there in Lorenzian CFT and interesting to think about. But in order to get there, I need to talk about how to lift operators to the embedding space. So I'm just going to explain that and then stop, because I know you guys are probably getting tired and want to go to lunch. The idea is that if you have an operator in Minkowski space that's a function of little x and little z, we can lift it to being a function in the embedding space. And the reason for doing that is because the embedding space operators have much more transparent conformal transformation properties than these operators. So I'll just write the dictionary, and then we'll start with that dictionary next time. So the idea is that if you have an operator O of x comma z, then you define an embedding space operator. And here for this, it's not important whether the operator is integer spin or not. The embedding space operator is defined as x plus to the minus delta O of little x equals capital X mu over x plus, comma, little z equals capital Z minus z plus x over x plus. So the reason for defining something in this really, really funny way is that it turns out if you use this definition, then if you start with an operator in Minkowski space, so a function of little x and little z that transforms like a conformal primary, then this thing transforms in an extremely simple way. So remember, a conformal primary has a conformal transformation property where if you conjugate it by the operator implementing conformal transformation, then it gets some rescaling and a rotation. And in our notation here, a rotation means that its polarization vector z rotates. So there's a position-dependent rotation of the vector z. This is a way of writing the usual conformal transformation law for spinning operators. And here, these omega and r are related to the derivative of the conformal transformation. So omega is the rescaling factor, and r is the local rotation that you get by doing a conformal transformation. And this is for some g in the conformal group. And so the claim is that if you have an operator that transforms in this way under conformal transformations, then if you build this embedding space operator, then it transforms under conformal transformation in a super simple way, where its coordinates just get acted on linearly by this SOD, 2 matrix. So this is something that you could, in principle, prove by taking this conformal transformation law, figuring out how all these things transform under conformal transformations, and putting them all together, and you would just, in the end, everything would simplify, and you'd just get this. So the advantage of building this object in this funny way is that it has this extremely simple conformal transformation law that basically linearizes the action of the conformal group. And this makes it really easy to write down conformal invariants for these operators in this language. And that's really, I should have said that earlier, that's sort of the main point of the embedding formalism. It completely trivializes the constraints of conformal invariance on correlation functions. Okay? Any more questions? Okay, good. I'll stop there. Thanks.